Hello, so thank you for coming to our talk. My name is Thomas, I go by swap.js on Mastodon. I started at Synactive, where I met Maxime, but then now I'm a principal application security engineer at Bentley Systems. We do infrastructure software for infrastructure, civil engineering, but this is my personal work, so if you don't like it, you can sue me, not Bentley.
Hello, I'm Maxime. I'm the co-founder of a cyber security company, which is called Fenrisk, and we provide penetration tests and trainings to our customers. I met Thomas, as he said, in another company a few years ago, and we started working together. Today we are going to talk about supply chain attacks. So, let's start with a little definition. A supply chain attack is a type of cyber attack that targets an organization by compromising a software provider of the victim. Rather than directly targeting a victim, a malicious tub of code is pushed into a software dependency, and the victim becomes vulnerable after updating or installing the source code, the malicious source code. A supply chain attack is rated as one of the 7 prime cybersecurity threats, according to ENISA. ENISA is a European cybersecurity agency, and supply chain attacks offers a great diversity of modes of action and are not limited to simple typo squatting on, for example, package names. A great research has been done and is described in the paper Taxonomy of Attacks on Open Source Software Supply Chains. It summarizes all the modes of actions available to perform a supply chain attack on open source projects. There are only a few examples of successful supply chain attacks exploited and detected in the wild. For example, in 2003, Gentoo mirrors were targeted. Attackers gained access to one of the mirror, and maintainers of Gentoo detected the attack, and within an hour, and the portage tree wasn't really affected. In 2011, kernel.org was also targeted. For those who don't know, kernel.org is the organization that manages the development of the Linux kernel. And attackers gain root access on the organization main server. In 2016, Linux Mint was also targeted, and attackers were able to change the legitimate link to ISO images on the forum to a malicious one in order to compromise users. Public researchers have also done their part of the job. For example, Thomas found ways to compromise Composer and Peer, which are the package managers of PHP, and he shows how to perform a supply chain attack on the whole PHP technology. And other technologies were also targeted, like Python or Ruby. And more recently, a case that is very interesting for us is the XEutils compromise. XEutils is a library widely used in Linux world by Linux distributions. And in 2024, a user who spent 3 years to become developer and later maintainer of the library started to push malicious code into this library. He pushed a backdoor that allowed him to bypass the SSH authentication protocol, and the backdoor was detected by an engineer of Microsoft who detected an unusual response time during the authentication protocol of SSH. We can deduce 2 things very important from this case. The first one is that the resources needed to perform such an attack by this way is huge. Because it needs 3 years of free work of developers to become maintainers of library, to start to push code. And the second thing very important is that all these efforts allow the attacker to compromise one single package of a Linux distribution. So the question is, today, what would it take to compromise an entire Linux distribution, and for example, by targeting their own infrastructure? To answer this question, let's have a quick look on how is the development model of Linux distribution. So Linux distributions are made up of a big ecosystem of many independent projects. Maintainers of the Linux distribution pull the code, retrieve the code of every independent project. Every project is developed by its own community. And developers, maintainers of the Linux distribution will then apply patches on these projects for security issues, for integration issues, for bug fixing, etc. And then they will have to build the packages. So in this example, the build process is a compilation step, a test step, a compression step, etc. Then a cryptographic operation is applied on the build package to ensure the users that it comes from the legitimate Linux distribution. So maintainers applied a signature on the package to ensure users that the package comes from the proper Linux distribution. Then the package is released. It is provided to the community, to the users that use it, makes a feedback to the developers, and it's a cyclic project. So, to perform a supply chain attack on the whole Linux distribution, we need to push a malicious code somewhere before the signing process, because we need our malicious code to look like a legitimate one. We need that our malicious package to look like a legitimate one. So we have only three choices. First solution, we could push a malicious code into a software dependency used by Linux distributions. That's precisely what attackers did in the XZ examples. And we saw that we cannot afford such a cost. The resources needed were huge, so we eliminate this case. Second solution, we could compromise the tool used by Linux distribution maintainers to manage all the source code retrieved from every different project. And this tool is hosted in their own infrastructure. And third solution, we could compromise the toolchain used by distribution infrastructure, used by maintainers to build packages, which is also hosted in their own infrastructure. So Thomas is going to present the methodology we use to achieve these goals.
Yeah, because we have achieved it, otherwise we wouldn't have a talk. Something I like when we approach this kind of project is that we don't want to be struggling. We want to do something fast, quick, have a quick win. We're not looking for any kind of exhaustivity. So we took this kind of plan of the infrastructure. We tried to identify weak points. That means storage of source code and building of source code. And some of this project is being developed by the targets, by the distributions themselves. They're not using GitHub or GitLab. They have their own Git fork sometimes. That means this project is likely to be unaudited, kind of custom one, just fit for their purpose, and also open source. That means we can more easily have a code review. I'm not saying it's less safe, it's just easier for us, lazy researchers, to have a look at it, deploy it internally, and play with it. So we only need one good bug. And the attack surface of this application is also a bit wider than usual, because everyone can be a contributor to a Linux distribution like Fedora, OpenSUSE, Ubuntu. Everyone can create an account and then access some kind of post-authentication attack surfaces. So it's going to be easier for us to access more features and maybe find more exploit in them. Based on our experience, we'll also know that some of this developer tool have kind of prevalent bug classes. And personally, it's the first time I'm speaking at Insomniac. It's going to be the third time I'm talking about argument injection bugs, just my personal favorite. I have in this link 1 hour rant at Greyhack on why this is the coolest bug class ever and why it's never going to be fixed. It just allows you, when a backend is invoking an external command, it lets you add new arguments, new flag to the external command. So it's not your usual kind of injection, like a SQL injection or command injection. You're not injecting instructions, you're injecting data that kind of changes the behavior of the program that's being called. There were about 200 CVs tagged with argument injection since 2004. I have at least 20 of these, and it's just the one which were disclosed and so on. It's no one's looking at it. I don't know why. It's really fancy and really easy to exploit. But to exploit it, it's going to depend on the capabilities of the colleague, because you're not injecting new commands, new instructions. You can only add flags. If you add the flag --help, it's likely not going to get you anywhere. You're going to get a help message, so no one really cares. But most of the time, you're going to be able to write like log files or get some kind of arbitrary file read or write primitive, and then try to get remote execution this way. So we're going to start to look at Pagure, which is what you've seen on the graph Maxime presented before, happening at the packaging step. So this is only for Fedora, which is one of the most popular Linux distributions. It's used as a upstream for CentOS, Stream, Red Hat Enterprise Linux. It's used as a base for CubeOS, which is like super secure operating system. It's used for Azure Linux, which is the Fedora remix for Apple Silicon laptops. You have like 100 million pools Docker for Fedora. I guess you already know the name anyway. And they host the sources of the packages that you can install in Fedora on their own software forge. They don't use GitLab. They use something called Pagure. There is a public instance on src.fedoraproject.org, and they have like 50 or 40,000 repositories. And within every single of these repositories, you can have several packages declared. It's only a small piece of the Fedora infrastructure. The graph you see on the right is coming from the Fedora documentation. So they list all the applications they deploy. And in this case, Pagure is something they call package sources. But you also see things like Body, Koji, Copper, which are custom made, so developed by Fedora maintainers application to build the project. They pull the sources and the descriptions of packages from Pagure, and they build it. And then they have also some later signing step. So to create your own RPM package that anyone on the Fedora distribution can install, you need a specification file, which is kind of like a make file. So you list all the build steps to assemble the upstream source and your patches and everything, and make a nice RPM archive. And then later you can go sign it. You also have a source file where you will be listing hashes, so more like checksums, all the upstream source code. But then you also need to develop your own patches. As a distribution, you want to get a good integration of this package, of the software in your own ecosystem. So you may need to provide small changes or sometimes entire new features. You can quickly cherry pick bug fixes from upstream just for your distribution to backport some bug fixes or some security issues. So you need to actually change the package you will be shipping to the users. It's practically never going to be the exact one from upstream. You always have your own distribution kind of layer around it. So if you compromise the platform, you get access to all these files, and you can just go change all these files. You would be able to change the upstream sources when they're not signed, which is the case for most of them. You will be able to change the patches, which are not signed at all. And all these things happen before build and distribution. So you basically backdoor this custom distribution source code layer around the upstream project right before signing. So this is what it looks like. It's just simple interface, like a simple GitHub, honestly. So we found a bunch of remote code execution in there. Otherwise, once again, we would not have a talk. Some of them are file system related, but we won't really care. If you want to play with it, you can easily diff it and try to find them again. Today, we want to look at the argument injection one. And the exploitation of these 4 bugs, or like individually, they all give you a way to access the bare Git repositories stored on the Pagure server. So the argument injection is in the log feature. So when you go like on GitHub, once again, doing the same comparison, but it's basically the same kind of model and features. You go on a file, you can see its Git history. So you will see all the different Git commits that happened on this specific file. And there's something we don't need an account to see the history of a file on GitHub. So this is the same thing here. And it's implemented in a way that you get this root being exposed. It's Python code. It takes the parameter called identifier, which is going to be a branch name, because your file could be existing on different branches. So you take the name of the branch from the parameter identifier, you pass it to the function called pagurerepo.log, And then you see it's building a git command line with git log and some options. And then your values that come from the parameter and then the name of the file. And then it runs the file. So the arguments to the git call are going to be pretty one line with commit, and then your injection point, and then the name of the file. And if you look at the manual page of gitlog, it's going to tell you, yeah, if you put the option -- output and the name of the file, we're going to write the history of the file to this destination file. So if we request this API endpoint and we say, okay, the identifier is in fact -- output tmp foobar, it's going to write the history of the repository for this file in tmp foobar. So it's kind of a powerful primitive. You can write semi-controlled kind of content at an arbitrary destination. Even if you don't have an account, you can request to write the history of a file that does not exist, and Git is still gonna create an empty file or truncate an existing file. So maybe we could have, with some time and effort, but maybe we're too lazy, try to find some file to remove or truncate, or try to find some kind of second order injection bug based on the file name to exploit this. But once again, we have an account on the platform. We are Fedora contributors like everyone else, so we can create our own repository. If you remember from before, there's going to be a prefix. So the commit ID will be prefixing the commit message. So we cannot guess the commit ID. It's going to be something we need to kind of live with, but we have control over the entire commit message. But if we try to override like a bash script or a Python script, we can maybe find some way to ignore this prefix, and then execute our command instead. So we did it like locally on the VM, but it was kind of like badly deployed VM. And when trying it in staging, with the approval, of course, of the owners of the project, it didn't work because all the Python scripts from the application itself, from the Pagure source code, are owned by root and were running as Git. So we couldn't override them. Instead, we tried to look at something a bit more interesting. And that, I need to tell you about the way it works when you git clone something over SSH. Like, when you go on GitHub, you git clone something, you can do a git clone over HTTPS or over SSH. And when doing it over SSH, everyone has the same username git. But everyone's coming with a different identity, and you need some plumbery behind it, after authenticating you to map your personal key to your GitHub account or your Pagure account to your privileges. So it's the same for Pagure. When you connect, the OpenSUSE daemon is configured to call the key helper.py script with the fingerprint of your key. If you have a Pagure user that exists with this key in the settings, it's going to let you pass, and it's going to force the command ACL checker. So you don't get a shell. It's only going to let you execute Git commands like git upload pack and git receive pack to send and receive data from the repository. So if you try to SSH like git at pagure.local, my testing instance, it's going to say, no, you can get a PTY, but it recognizes me. It's saying, welcome, Thomas, but I don't give you shell access. But if you kind of trace the process, you will see the first highlighted line is key helper. So this is SSH trying to match my fingerprint of my key with my identity on Pagure. Okay, I'm authenticated. It knows me. It knows I'm Thomas. But then it's going to forward the command ACL checker to run to verify if I am allowed to access this specific repository. And in doing this, SSH is going to run the command in the user's shell. That means bash. And bash will be loading the .bashrc file when starting before executing the ACL checker command. That means if we override this bashrc file with our firewrite primitive, we're going to be likely to be getting a shell. We already discussion that, yeah, maybe they did it wrong. Maybe they could have been putting like bin false or bin no login as a shell, so this thing wouldn't happen. But then you would not be able to execute any of the commands because at this step, the third step, SSH would say, no, you don't have a shell. I cannot run ACL checker for you. So it's maybe a design problem, but it's not going to be a straightforward one to fix. So the exploitation is honestly just a request. You create your repo. You call this API root with -- output, srv git.bashrc, and you override it. You have this prefix, which is not a valid git command, but then we started using the pipe operator that says, okay, the command cc55d10 is likely not to exist, so it's going to return an error code. But if it fails, run bin bash instead. So really simple, we create an account on target, we add a public SSH key, we create a repository with at least one commit, whose message is pipe bin bash. We exploit the argument injection, we overwrite the file, and then we connect over SSH to get our shell. So I got a quick demo just to show you. It's 1 minute 30, but it's really what it takes to exploit it. So if I try to connect, okay, it's telling me I don't have a shell, which is the usual expected behavior. I go on my Pagure. This one is a local instance. I create my project. So Demo Insomniac. Typing is just honestly the slowest part of this demo. I create my README, and then I can go directly edit my README file to add my new malicious commit with my malicious commit message. My pipe bin bash, I create my commit. My history is kind of poisoned, and now I can go into history feature. I put my argument injection, so -- output equals srv bin bash rc. Okay, it fails successfully, I guess. And then if you log in, you get directly an error message saying me, oh, okay, command not found. So it's trying to execute the command that would be the git commit ID, so which is already a good start. And then if I start typing my commands, I get my shell, and everything works. Just for the demo, I try to do something where I add some kind of other repositories, in a private one, just to show that, yeah, you get on the file system access to all the other repositories. In this case, we get admin, and they have a super secret repository, but obviously you get read-write access to any of the repos on this thing. And if you close the shell, it says, yeah, I don't give you shell access, because then it executes the SQL checker thing. So this is just like to show off just on the staging instance, just prove it works. And good thing is it's a simple bug. And I was like, oh, maybe it's going to be super complex to disclose and it could be a mess and everything. The timeline is a bit weird. January 1st finding. I was maybe too lazy to exploit it for real because it didn't work on staging, but then reported it. Anyway, they patched it within 3 hours when they got the real report of RC, which is just phenomenal. We were kept in the loop. We reviewed the patches. They were like super nice. And it was the first release in quite some time for Pagure. So it kind of made the project a little bit alive again. But it's just a one-off fix, and all of the fixes, they never really fix the root code. In this case, they still sometimes invoke git commands, while they could be using the libgit2 library bindings, which are not relying on an external command, which would kind of throw out the risk of argument injection. But I think one of the reasons is that they plan to move away from Pagure and try to move to a new forge. So I'm not saying this is because of us or thanks to us, because I don't think it's related. It's been like into plans for a long time. And then when I moved to something called Forgero, which is a new Golang-based Git forge, basically, once again, a GitHub clone or GitLab clone in Go. But they want to self-host it, so that means still there could be some misconfigurations, some patch gaps. I don't think it's going to be a silver bullet. And if you try to look for Forgero CVs, you're like, okay, so they never had any CV. Are they super safe? No, they just don't publish CVs. They have their own advisories on their own issue tracker. So it's kind of hard to really sense if this project is super secure or not. Could be a good idea for next target. And also it's a fork of Git-T, which is itself a fork of Gorgs, and we got honestly, basically the same bugs in Gorgs last year, like exactly the same symlink attacks, exactly the same argument injection attacks. So they built on kind of like shaky foundations. So we'll see over time if they achieve to keep it safe and kind of prevent these kind of attacks from happening over again. And now Maxime is going to talk to you about the building step.
Well, Open Build Service, OBS, is a full tool chain initially developed by the OpenSUSE project, which is also responsible for the development of the Linux distribution OpenSUSE. This tool chain is used to build, it's an all-in-one tool to build packages. It manages packages formats to fit a large set of Linux distribution like Red Hat, Debian, etc. OBS is used by around 20 downstream distribution, related to OpenSUSE, but it's also used by companies such as Dell or Intel or projects like VLC. And the instance used by OpenSUSE is located at build.opensuse.org. The instances used by Dell or Intel are not exposed to the internet. OBS offers a web application, a Ruby on Rails web application, which is responsible for user authentication. So everybody is able to register a user, to connect to manage his own private space, to create packages, to download sources to the packages directly, or to tell the application to retrieve sources from third-party servers, using, for example, Git or wget commands. And then post-process are also available, like for example, tarball extractions, etc. And then the application allows the user to build packages and to retrieve the build package. The architecture is pretty simple. The users interact with the application using the front end or the API through a CLI. Then sources are managed by source server. The scheduler is able to detect the need of launching a new build. So he is able to detect source modification or for timeout matters. And then the scheduler tells the dispatcher to launch a new build. The dispatcher chooses a free worker. It creates the proper build environment in this worker. And then the worker builds the package and sends it back to the user through the publisher. The vulnerability we found in this application is an argument injection, another, in download URL script. This script is responsible for downloading source files from a third-party server using wget. So when I'm a user, I've got the context of my package. I'm able to trigger the execution of download URL by sending a service XML file formatted like that. When such an XML file is used, the application is able to parse the XML file to retrieve the download URL, the name of the script, and then parameters to apply it to the script. In this case, the URL pointing on server.com, port 5000, etc. In this case, for example, the application will launch download URL script with the parameter with the arguments set in the XML file. So in this case, http server.com, etc. And then the download URL is a bash script. So it will call wget with the URL specified. At this point, the URL, the application is vulnerable to argument injection. It's vulnerable because an URL could be replaced by an arbitrary argument valid for wget. The problem for attackers, that the vulnerability is not exploitable. Why? Because wget needs a valid URL to be successful. Otherwise, it will fail into an error missing URL. So if I change the URL with an argument, I won't have a real exploitable argument injection. Looking at the download URL sources, we found another option very useful in this case called download manifest. This option is interesting because download manifest will tell wget to look for his URL in an input file. So, and it will look for the input file in the context of the package. So, in my package, as a source file, if I upload a TOM file containing a URL pointing on resources on the internet that I control, I will be able to specify to the application to find his URL in a TOM file using the download manifest parameter, and I will be able to replace the URL argument by an arbitrary argument and to have a successful injection. In this case, for example, the wget command executed by the application will become wget input file, the temp file, in which a URL is available, and then output document tmp test. In this case, wget will generate a request and will write the result of the request in an arbitrary path, in an arbitrary file name with an arbitrary content, because I control the URL specified in temp file. So it's an arbitrary file write on the server. Another way could be to inject another argument, which is post file. In this case, wget will generate a request to the URL specified in temp file with as content the content of the file in the argument. In this case, etc pass wd. So in this case, I've got an arbitrary file read from the server. So to sum up, I upload my temp file with evil.com evil file. I trigger the argument injection by uploading the service XML file containing, for example, the output document argument. Then the application generates a request to evil.com and retrieve the content of the file, and the content of the file is written in the argument in the arbitrary path specified in the service XML file. So I've got a read and write file on the server, and I would like to transform this read file and write file to a full and complex remote code execution. So, very interesting argument. Another argument of wget is very helpful in this case. It's called useAsPath. UseAsPath tells wget which binary to use to ask user for his credentials. So, if I run wget with useAsPath pointing to usr bin id binary, wget will call a US bin ID as a sub-process. The problem is useAsPath is incompatible with the input file options. So both options cannot be used at the same time in the same command. So the solution to do that is to write a wget rc file, a configuration file used by wget, and loaded from by the binary, and to specify the useAsPath option in the configuration file. The second problem is that useAsPath allows the attacker to launch a single binary but without argument, and we would like to have a full and complex remote code execution. So the problems are: it's impossible for us to write and then call a binary. I'm not able to write a file and then call it because a matter of execution right. It's impossible for us to replace an existing configuration file or binaries. So I'm not able on the server to modify binaries or configuration file. I'm not neither able to modify the OBS sources, the OBS script. There are no cron job or scheduled tasks to modify to have to trigger a command execution. I'm not able to exploit this vulnerability as Thomas did on Pagure because my server is not a Git server. I have no SSH exposed, and the solution we started to find is to look for binaries that loads a configuration file from the home directory of the user. Why? Because that's one of the only directory we are able to write in. And the second criteria is to look for binaries that have an option that triggers the execution of something. And we found one binary very useful. It's called prov. Prov is a Perl test manager, and prov has an option which is exec command, which will exec something, and it loads by default a prov rc file from the home directory of the user. So in this case, our exploitation become a 3-step process. First step, I write a proverse in my configuration file proverse containing an exec of an arbitrary command in the home directory of my user. Then I write a wget.rc file, which will be loaded by wget, which contain the useAsPass option. And then I call wget without the input file argument to trigger the load of, in this case, wget will load his wget.rc file. It will execute the useAsPass. useAsPass will be configured to point on prov binary. Prov will be launched. Prov will load his proverse configuration file, and then will exec the exec command specified in the proverse file. Demo time. Sorry, the demo is video because, you know. So, on the right screen on the top, this is my evil server, so my server control. I have a proverse file which will launch an arbitrary TMP script file. TMP script will do connect back on my server with on the port 10,000. Sorry. wget.rc file will have the useAsPass option with pointing on prov binary. Then on my own computer, I write some files to point on each resources. So my HTTP server is listening. I create a package. I had a source file with stage 1 pointing on wget.rc, stage 2 pointing on proverse file, and then stage 3 pointing on my arbitrary script. Then I upload the service XML file, and the application comes back and retrieves the content of wget.rc. So wget.rc has been written in the home directory of my user. Then I did the same thing with proverse file. Then I write my arbitrary script in TMP. And then I have to listen on the proper port number for my connect back. And then I launch wget. And the shell comes back. So we found the bug the 27th of June in 2024. 2 days later, we reported the bug to OpenSUSE. They confirmed the bug the 1st of July, and they had a successful patch 10 days later. Thomas will conclude.
Yeah, so it's conclusion with S, because I have two conclusions, one from the offensive side, one from the defensive side, depending on which side you are. It felt too easy from the offensive side. Honestly, all the bugs are silly. I was like, maybe it's not good enough for Insomniac, but the impact is terrifying. Like, we proved on these staging instances that we could effectively get RCE and change any of the packages of any of these distributions, likely impacting all the users if it's not detected on time, and also affecting the downstream distributions, and like it's an entire mess. So it felt super easy compared to XZ, where it was likely a team effort of people actually working, actually contributing to the project, becoming maintainers to put the backdoors. It was just like orders of magnitude simpler. I think one of the reasons is that we approach it, like I said, being lazy, trying to say, okay, let's take the weakest point of the infrastructure. Let's come with this bug class already in mind. So we already know what we are looking for. It's kind of like CTF mindset, where you know there is something, we'll find something. eventually. And once again, argument injection, just my favorite personal best thing. All languages, all APIs, no easy mitigation. Yeah, because I think I'm going to be making a living out of it for quite some time. And hopefully everyone else too. And also, I think we're not the only one interested in this target. It was just for fun. Like, we're not just messing around. We actually paying all the maintainers before getting a shell on the real machines. We were not just being malicious at all. But we already have a few detected in the wild cases. Like at the beginning, Maxime covered all the detected in the wild compromises of infrastructure of OpenSUSE project, but it's only going to be a subset of the actual one. I don't want to be, fear-mongering and say, it's only 10%. We don't know, but it's a fact. It's just less than the actual one. And this one's being quite easy. I would assume that, it's definitely not all of them that are being detected on time. It would be, we try to theorize it for Dashen states. Can you just exploit it and deploy backdoor on hundreds of millions of machines? I think it would be, from my unexpert opinion, not a lawyer, everything, dubious legally. You would compromise your own companies, your own citizen, everything. But if you're a ransomware actor, you don't care. You just want to make money, so who cares? And we've also seen that brokers are buying SCM exploit. There are public brokers, some of them with ties to Russia, saying, we want to buy your GitLab 0-day for $50K. So definitely people want to get this kind of accesses. Maybe not as wide, but at least to be able to target people through supply chain attacks on source code hosting repositories. On the defensive side, we try to put our defender hat on. What can we do to prevent it? Honestly, not much. Some much more expert people, like the ones working on the SALSA framework. It's a build attestation framework trying to help organize this project to most of the time add attestations, and they kind of give a general framework to help you make your supply chain as a person building project and distributing project to make it more secure by signing. But you cannot just sign the file at the end of the process. Like we've seen, it's not enough. You need also to attest source code. You need to attest basically everything the distribution is building for this project. And interestingly, the SALSA spec says, if you compromised Pagure, if you compromised GitLab, it's game over. It's out of scope. So there's still some work also to do here. And I don't think we can realistically expect every single of this project to add a really state-of-the-art attestation mechanism, because you would also require all the upstreams to be signed, and you cannot go ask some random project hosted on on FTP somewhere in some country you never heard of to go sign with a release with GPG all the time. It's not realistic to say that all the upstreams would be signed and attested. Though if you compromise Pagure, even if the distribution patches are signed, you would still be able to alter the upstream code and put your backdoor. For OBS, it's slightly different. I think you don't need to get the pre-built packet for you. You could just build it yourself. You can have your own OBS instance internally and build everything. So you would kind of remove this risk. Still not perfect. Also, as an industry, we tend to say, I don't want to get any CV in my project, in my dependencies, but it doesn't really make sense, I feel like, all the time. ZRI is kind of weird on this. But these tools, of the SCA tool, SBOM tools, they can help you to understand how exposed are you? Which supply chains are you depending on? Are you pulling your Python packages from PyPy or from your distributions? It changes a lot. And then if you see, we are only dependent on Fedora for everything, let's, pay for audits for Fedora infrastructure. Let's sponsor features. Google, and I think the Sovereign Tech Fund, paid the company Trail of Bits to implement digital attestations for PyPy packages a while back. It's a good effort. Google wants to see this implemented. They pay for it. They design it. They help design it, and you bring some security companies with this knowledge on board, and you end up with I think, pretty good attestation system for Python packages. But then you need to do it for every single other supply chains, and it's just not realistic to do it this way, and we cannot expect Google to pay for every single one of these. And honestly, I say it's silly, I say it's easy to find, huge impact, but it doesn't mean these distributions are any less safe than others. It's just that we found Fedora OpenSUSE and we stopped because it was good enough for us already. But they were honestly one of the most personally, but I think for you too, it's just like one of the most reactive and efficient disclosure ever. On my case, I was the one taking my time to answer and reply and forgot about the thing, but they patched in production within 3 hours, which is honestly unheard of even on like big companies. So they are like actually, I think, really safe, and the maintainers are working really well. And this talk is in no way to say Fedora or OpenSUSE are any less safe than any other distributions. It's just an anecdotal data point and not just like something to generalize and to say that any less safe. So thank you. If you have any question, I think we have some time for questions, or you have our email addresses and social media here, and feel free to send us a message. Thank you.
Okay, we have 2-3 minutes for questions. Yeah.
Thank you for a very interesting talk and making my nightmares so much colorful. You work in RPM family of distributions. Do you have any indication that we could extrapolate to Debian family as well?
Yeah, it's just infrastructure. You just find a weak point and you get in. And I think if you cannot guarantee attestations for your upstreams, for patches, for everything you produce, it's game over anyway. But I would tend to think, without any evidence, to think that Debian is a bit more conservative and will likely have less things exposed from what I've seen. But once again, we've not really tried to get into Ubuntu or Debian or any of the other ones. As we've seen, like Gentoo was at 2003 by like this rsync, RCE. What can you do? People at Google just released a new rsync exploit. They could have been exploiting it. I don't think they did, but they could have been exploiting it on the distribution mirrors, like it was the case in 2003. So it's bound to happen. I think it's okay to live with it, but just to maybe reduce exposure and say, okay, we trust Fedora more than Ubuntu, so we're just gonna go only on Fedora and not use Ubuntu for anything. But it's a decision you need to take, and it's never going to be solved by any security product or anything.
We have time for one more question.
Nice talk and nice findings. And I was wondering, in both of the vulnerabilities, you end up with an RCE, but reducing the privileges of the users that you find an RCE would somehow mitigate already these findings, or would it break like the whole design of the application, because then those users couldn't do what they were intended to? So like, would it be possible with just reducing privileges to kind of fix these issues?
Yeah, I think it would be a good practice, but for Pagure, if you go on the web UI, you're going to be able to edit files, to read files. So you need basically file system access to all these files. So they are all owned by the Git user. So you could try to make different system users for everything, but then it becomes complex. We haven't really tried to LPE because it was not, I think, not fair. We were just auditing the apps. We found the bugs. We reported the bugs. We're working with the maintainers who were not trying to be malicious. And if we would have gotten root. Maybe it could have been something, but not really as part of the assessment. I think we can go with safer designs, but it's never gonna, you're only gonna try to limit the risk, but you're never ever gonna be able to solve it in this case.
Thank you, Maxime. Thank you, Thomas.
Thank you.